Hello everyone, my name is Adisak Maumisi. I'm from Khon Kaen University, Thailand. Today I'm going to present my research in the title Bayesian's bonus Malus premium with Poisson Lindley distributed came frequency and Lognormal gamma distributed came severity in automobile insurance. Today I would like to present in the following items. Firstly, I'm going to talk about introduction and motivation. After that, I will talk about research methodology. In this section is separated into two subsections for claim frequency distribution and claim severity distribution. Then, I will talk about the numerical application, which illustrated and the results are discussed using the real claim data, separate as claim frequency component and claim severity component. And finally, I will conclude. Let me start by introduction and motivation. Risk is uncertainty that can occur and can measure the uncertainty. The uncertainty can lead to loss or claims. As a result, it causes a guarantee of the risk, so causing insurance company with a busyness that is receiving a lot of attention nowadays. Insurance is the transfer of risk between the insured and insurer under agreement or contract. The insured will be protected according to the contract. At the same time, the insured will receive insurance premium in return. There are many ways to calculate insurance premium. Here, I'm interested in bonus Malus system, which used to determine insurance premium. This system is used to determine insurance premium in many countries, especially in Europe and Asia. And this system is used to reduce accident loss in car insurance. This traditional system considers only the number of accidents. If the policyholder makes claim one or more times, they have to pay more premium in the next period, which called Malus. But if they don't make any claims, they have to pay less premium in the next period, which called bonus. Moreover, it depends very much on the historical claim records. The purpose of this system is to reduce the insurance premium for drivers with a good driving behavior and to increase insurance premium for those who are not careful when driving. However, all accidents don't make the same severity claim. So, when policyholder makes a claim, it seems unfair to penalize all policyholders in the same way. Therefore, in this study, I consider calculating the premium based on bonus Malus system by regarding both the number of claims and the claim size. The premium estimation is based on the net premium principle as the product of the mean of the Poisson distribution function for frequency component and Poisson distribution function for severity component. In this study, I propose a new claim frequency distribution and claim severity distribution to determine optimal premium based on bonus Malus system. The number of claims is considered when mixing the Poisson with Lindley distribution to assess the claim frequency distribution. The Lindley distribution usually has the thicker tail than exponential distribution, so it should provide a better fit to the claim dataset. To increase clarity, I use the Poisson-Lindley distribution for claim frequency distribution. While fitting values are compared using the real dataset for claim severity distribution, the claim size in automobile insurance is usually heavy tail distributed. Many previous studies use the Pareto distribution to model claim severity. However, Pareto distribution doesn't adequately fit to the claim data. Other heavy tail distributions such as gamma and log normal distribution are appropriate to model Kame severity distribution. In this study, I propose a log-normal gamma to model the Kame severity distribution. Next, I will move on to the research methodology. This section I will separate into two subsections for Kame frequency distribution and Kame severity distribution, and assume that the frequency and severity of Kame of each policyholder are independent. Each subsection, I'm going to present at the following step. The first step, I will talk about the mixing distribution, which provide a better fit to the Kame data. After that, estimate the parameter of mixed distribution and use the goodness of fit test to test the model. Then, use the Bayesian method to obtain the Poisson distribution function. And finally, price the insurance premium. The Bayesian bonus Malus premium that must be paid fairly for all policyholders in the portfolio is equal to the product of the Bayesian premium with both on the frequency component and the severity component. In automobile insurance, all policyholders have a constant as an unequal underlying risk that an accident will occur. The constant is called the least parameter and is treated as a random variable that depends on each policyholder. The distribution is called the prior distribution. Mixing the Poisson distribution with the prior distribution gives thicker tail than only the Poisson distribution. So, the mixed Poisson distribution compared with Poisson distribution provide a better fit to the Kame frequency data. So, I propose mixed Poisson distribution with Lindley distribution to model the frequency distribution. Assume that the number of K is distributed according to the Poisson, given parameter theta with the probability mass function at the following equation. And the expected value of the Poisson random variable is equal to theta. All policyholders have a constant representing the expected inherent risk of each policyholder. This is the mean of the number of claims of each policyholder, denoted by theta. Assume that theta is distributed according to the Lindley distribution with parameter delta. Then, the probability density distribution or PDF of theta can be represented at the following form. And the mixed Poisson with Lindley distribution is obtained at the tail below. The maximum likelihood estimation or MLE is widely used to estimate model parameters. The basic idea is to choose the parameter value that maximize the likelihood function, which the probability density of the observed data. The principle of the maximum likelihood is to estimate the value of the parameter that make the observed data most possible. The methodology of MLE for Poisson-Lindley distribution is presented as follows. Let K1, K2, 2Kn be random sample of size n from the Poisson-Lindley distribution. To find the most likely value of the parameter delta require maximizing the likelihood function L, where L is equal to like this. Then the log likelihood function is equal to like this. The estimated delta hat of the parameter delta can be obtained by solving the equation. And we have like this. And finally, we have the last equation. Because the estimation of the parameter delta can't be found in the code form, the numerical iteration technique, that bisection method, is used to solve in the last equation. For the frequency component, the chi-square goodness of fit test is used to describe how the observation of a given phenomenon is significantly different from the expected value. Chi-square is used to compare the observed sample distribution with the expected probability distribution and how well the theoretical distribution is suited to the empirical distribution. The sample data is divided into intervals. Then the number of the points that fell into each interval are compared with the expected number of points in each interval. The value of the chi-square goodness of fit test is computed using the following formula, where x power 2 is the value of the chi-square goodness of fit test. OI is the observed frequency count for the I level, and EI is the expected frequency count. The bonus Malus premium calculation has been studied using several methods, with Bayesian methodology as one of the most popular methods. The main purpose of the approach is to obtain the Poisson distribution function. The Bayesian methodology can be applied when the data for each Poisson holder is available, whether based on claim history for previous period or Poisson holder profile. Let K be the sample where T is the sample size, and let N is equal to summation of Ki for I equal to 1 to T to T with the total number of claims made by a policy holder over T years, where Ki is a number of claims that the policy made in the year I for I equal to 1 to T to T. The likelihood function is like this, and the prior distribution is equal to in the last equation. Then the Poisson distribution for a policy holder or a group of policy holders with claim history K1, K2 to KT can be obtained by applying the Bayes theorem. The Poisson distribution function is proportional to the product of the likelihood function and the prior distribution. Consider the proportional. Then we get this equation, where A is a constant. We can calculate the constant A like this. So, the Poisson distribution function for frequency component can be expressed by in equation. Next, I move on to premium calculation. Many principles are involved in pricing insurance premium. In this study, I determine the net premium principle. This is the basic principle in the sense that premium should be expected value of loss. The net premium in such a situation is the expected number or mean of the number of claims that occur from each policy holder. The expected number of claims of a policy holder with a claim history K1, K2 to KT, or the mean of the Poisson distribution function for Poisson-Lindley distribution will be like this. Assume that the initial premium or base premium at time t equal to 0 is 100. Then, at time t plus 1, The premium can be determined from the number of chem and expressed as the following form. Now I'm going to present the chem severity distribution using log-normal gamma. In an insurance portfolio have retail distributions such as gamma, log-normal, Weibull, Pareto, and Burr are commonly used to model chem severity distribution. Since mixing these chem severity distribution with a prior distribution give thicker tail, the mixed chem severity distribution provide a better fit to the chem severity data. In the literature, mixed exponential distribution has been widely used to model severity distribution. In this study, I propose a mixed log-normal distribution with a gamma prior distribution to model severity distribution. Let X be the random variable of the chem size of each insurance person. Assume that the size of chem X follow the log-normal distribution. Then the PDF of log-normal distribution is given by, and the expected value of X will be equal to like this. The parameter lambda has different value according to each Poisson holder, so it is reasonable to expect lambda as a distribution. The gamma prior distribution for lambda with parameter alpha and beta has the PDF as the following form. So, unconditional distribution of the chem size X can be obtained at the following below. The methodology of the MLE for log-normal gamma distribution is presented at the following. Let vector X be an identically independent observation for log-normal gamma distribution. To find the mostly likely value of parameter alpha and beta that produce outcome X, the likelihood function L must be maximized, where the likelihood function L is equal to like this. Then, the likelihood function is provided as the following equation. The estimated alpha hat and beta hat for alpha and beta respectively are obtained by this equation. Then, we have this equation like this. Since the estimation of the parameter alpha and beta can't be found in closed form, the numerical iteration technique is used to solve them. AKA information criterion or AIC is used as the model selection criteria. The minimum AIC illustrated a good model among all the authors with a better fit to the chem data. The equation used to estimate the AIC of the model can be expressed by like this, where L is the value of the likelihood function of the model and M is the number of estimated parameters in the model. In this study, I used the AIC to measure the relative quality of the statistical models for chem severity distribution. The total number of chem that a Poisson holder makes in T years is represented as N, which is equal to summation of Ki, which I equal to 1 to T to T. Let Xk denote the size of chem K for K equal to 1 to T to N. Then, the chem size history in T year can be displayed in the form of the vector X. The total campsite over t year is summation of ak for k equal to 1 to t to n. Then the likelihood function is like this. And finally, the pi or distribution is in the last equation. By applying Bayes' theorem, the posterior distribution function is proportional to the product of the prior distribution and the likelihood function. That is this equation. Consider the proportion. Then we have in the equation where b is a constant. Then we get b like this. The posterior distribution function for severity distribution can be presented in the following form. For Km severity distribution, I use the net premium principle for computing the premium similar to the Km frequency distribution. The expected value of log-normal gamma distribution is like this. From expectation of lambda given x1, x2 to xn is equal to lambda hat. Then the expectation of x1, x2 to xn given lambda is equal to like this. So the expected value of log-normal gamma distribution is equal to this equation. The suitable premium that each policyholder pays must be proportional to both the number and size of the claim. The exact loss, xk according to form, each claim result in different premium for policyholder with the same number of the claims. The Bayesian bonus malus premium that must be paid fairly for all policyholders in the portfolio is equal to the product of the Bayesian premium based both on frequency component and severity component and can be expressed by like this. To determine the bonus malus premium for a policyholder that must be paid according to the purpose model, we need to know the number of claims, age of the policy, claim amount, and total claim amount. All these values are generally shown in the portfolio. The Bayesian bonus malus premium at time t equal to 0 is called the base premium, this initial premium that a new policyholder who joins the insurance must pay. Because of no claim at time t equal to 0, in this study I consider log x 0 equal to mu. So the base premium can be expressed by like this. Next, I move on to the numerical application. The data set is applied based on 1-year automobile insurance policy taken out in 2004 or 2005 to calculate the model premium introduced in the study. There were like this policy in the total portfolio. First of all, I will provide the result of bonus malus system based on claim frequency component. Claim frequency distribution is applied by Poisson-Lindley distribution introduced in this study. The maximum likelihood estimator of parameter of the Poisson-Lindley distribution is like this, with chi-square goodness of fit test is equal to like this. I compare value of observed claim frequency between traditional Poisson exponential distribution and a Poisson-Lindley distribution. Results show that the Poisson-Lindley distribution give a better fit to the data than Poisson exponential distribution. The bonus malus premium based only on the frequency component are determined and calculate will result to interval 2. From result interval 2, a bonus with no came in the first year represented 6.74% of the base premium. On the other hand, policyholders who made one claim during the first year must pay a malus at 85.92% of the base premium. Premium decrease if the policyholder had a claim-free year and increase if the claim occurred. Next, I will provide the result for bonus-malus system based on both the claim frequency and claim severity component. I will restate the premium using the purpose model. For estimated parameter based on severity component, I fit unconditional distribution as a log-normal gamma distribution to the claim size. Some symbols are defined for the purpose of convenience of explanation. I define NC as the number of claims, CS as the claim size or severity of claim, and TCS as a total claim size. I illustrate some cases where the amount of claim of an interest is different. I consider the case of a policyholder who made 4 claims amounting like this. This table shows the premium due for various claims when the age of the policy is up to 7 years. Claim size were like this. The base premium computed is equal to like this, and this decreased with a claim-free size, a claim-free year. On the other hand, if there is an accident with a claim size of 235 in the first year of observation, the policyholder will pay like this. If a policyholder makes 2 claims in the first year, with the first claim is 235 and the second claim of 471, then he or she will pay like this. The premium increase as the number of claims increase. If in the second year the policyholder does have an accident, then the premium will reduce to like this for the number of claims from 1 to 4 respectively. If the policyholder no longer has any claim, the premium will again reduce for the 3rd year, the 4th year, and so on. Okay, in this study, a model is purposed to determine bonus-malus premium. The model considers both claim frequency and claim severity component. Two mixing distribution as a Poisson with Lindley distribution and mixed log-normal with gamma distribution are investigated and employed in the model at frequency distribution and severity distribution respectively. The premium is calculated by utilizing the Bayesian method. I use an example of real automobile insurance data to illustrate my model. The fit result of claim frequency are better than those traditional Poisson exponential model. This approach offers a fatter method of penalizing policyholders in the portfolio. Thank you for your attention.